Solutions are homogeneous mixtures. So just to review, we have two different categories for mixtures. A mixture can be a heterogeneous mixture, and those are a type of mixture in which you can actually see the different components on it. When you have a homogeneous mixture like a solution, a homogeneous mixture actually looks like a pure substance. You still have more than one component in the mixture, but you cannot actually see those different components in the mixture. A mixture can actually be separated by physical changes. There's no reason on why decomposing a substance or converting a substance into something different when you're trying to separate the components of a mixture. If you have a mixture containing different liquids, you can actually separate the different liquids in that mixture based on their boiling point or evaporating one of the components in your mixture using distillation, which is that kind of separation using the different boiling points of the liquids in the mixture. The two components in a mixture are the solute and the solvent. That doesn't mean that you have only two things in a mixture. You have two components. Okay? The solvent is whatever you're using to dissolve the solute. If the solvent is what you're using to dissolve the solute, the solvent it's always in a greater amount because it's doing the dissolving. And then you have your solute, which is what you're dissolving in the solvent. Now, these are the two components of your mixture. It's not that you have just two things, one solute, one solvent. You can have a solution containing two solutes dissolved in one solvent. You can have solutions containing one solute dissolved into two different solvents. Okay? So the number of solute and different solvents that you have, that's not the main idea. The idea is that you have these two components, things that you're dissolving and things that you're using to dissolve. And just like some definitions here, when a substance dissolving another substance, we're talking about the solubility. If something is not soluble in another substance, then we say that that substance is insoluble. For example, oil is insoluble in water. They have different intermolecular forces, so you cannot dissolve oil in water. You cannot prepare a homogeneous solution using those two components. If you add a liquid into, let's say, for example, water, and that liquid is soluble in water, then we call them miscible. Okay, when you have liquids that are soluble in other liquids, we call them as miscible. Ethanol is an example of a miscible liquid in water. Okay? So you can add ethanol to water and then they will create a homogeneous solution. You don't get to see, the ethanol inside the water because the mixture is homogeneous. In general, the solubility of a substance that is a solid at room temperature in water increases as the temperature increases. For example, if you can dissolve 30 grams of a specific compound in 100 grams of water at room temperature, if you increase the temperature of the water, let's say to 50 degrees Celsius degrees, then the amount of that substance that you can actually dissolve in the same 100 grams of water will be greater than 30 grams because as you increase the temperature, we can dissolve more solid in water. When we're looking at the solubility of gases in water, for example, we don't think too much about dissolving gases in water, but gases are soluble in water. We create solutions containing hydrogen chloride in water to create hydrochloric acid, for example. And there's oxygen dissolved in water, there's nitrogen dissolved in water. So gases are soluble in water. Now, the solubility of a gas in water is going to depend on two things, temperature and also the pressure. Contrary to what happens to the solubility of a solid, when you have a gas dissolved in water, as the temperature increases, the solubility of the gas decreases. When you're increasing the temperature, what's happening is that the molecules are gaining kinetic energy, right? Or thermal energy, which is a type of kinetic energy. And then the molecules will gain enough energy, right? And that amount of energy will be enough for the gas to escape the liquid. That's why when the temperature increases, the solubility of a gas decreases because now the gas will have enough energy to actually leave as a gas. It will be removed from the solution because it's gaining energy that is going to allow those molecules that prefer to be a gas at room temperature to escape from the solution. Now, when you're looking at the pressure, increasing the pressure actually increases the solubility of a gas. When you're increasing the pressure, you're forcing the gas to stay in the solution. Before we start talking about how a solution can be created, let's talk about the type of solute that we can have. And when I am referring to a solution, we are looking at different types of solute dissolved in water. So water will be acting as the solvent. Even if I don't mention it, then you should remember that I'm referring to water as a solvent. We have compounds that can be classified as ionic and compounds that can be classified as covalent. That's going to depend on the type of chemical bond that we have in those compounds. When you have a chemical bond in which electrons are being transferred, you're forming a chemical bond between ions, and those are ionic compounds. When you have a chemical bond in which the electrons are being shared, what you have is covalent bonds. Okay? The electrons are being shared, and you have a covalent bond, which is a molecular or covalent compound. Now, an easy way for you to identify a compound as ionic or covalent, right? So you can have an idea of the type of solute that you have in your solution is actually looking at which elements you have combined in your compound. In general, when you have nonmetals bonded together, or metalloids with nonmetals, the type of compound that you have, it's a covalent compound. For your ionic compounds, you will have a metal combined with nonmetals or metals combined with polyatomic ions, or you might have NH4 plus, which is ammonium, combined with a nonmetal or with polyatomic ion. So let's make some notes in here. So you have the summary, okay, of the type of solute that you can have, ionic or covalent. The type of solute that you have, right? If it's soluble in water, we can predict the solubility of ionic compounds based on the solubility rules, and we can predict the solubility of covalent compounds in water based on intermolecular forces. The solubility based on intermolecular forces, what we use is that substances that have similar intermolecular forces as water will be soluble in water. For example, water is a polar molecule. You have the polar bond between the oxygen and the hydrogen. You have that charge separation because the oxygen is a lot more electronegative than the hydrogen. So that oxygen pulls those electrons in the chemical bond towards itself, creating this charge separation in which you have a dipole in your polar bond between the oxygen and the hydrogen. So the molecule for water has your polar bonds and it's actually a polar molecule. So we're expecting that substances that are polar can be dissolved in water because the the intermolecular forces will be similar. Ethanol is soluble in water because in that molecule you have an oxygen bonded to a hydrogen, which is a polar bond, and we do have similar intermolecular properties, so the ethanol is expected to be soluble in water. Now, the solution process is going to depend on the different types of interactions that you have, right? If you have just water, right? Let's say you have a beaker with water. All of the molecules in your beaker are molecules of water. So you do have interactions between your solvent molecules. So that's the first type of interaction that you have. Solute, solvent, solvent, right? Because we're looking just at a beaker containing water. If your solute is, for example, the the ethanol, right? And you have like a little beaker with some ethanol in there, your ethanol molecules, they have interactions between them. So you have your solute because we're dissolving ethanol in water, right? So when the ethanol is by itself, you have interactions between the ethanol molecules. The water is by itself, so you have your interactions between the water molecules. So you have solute between the ethanol molecules, and then you have solvent between the water molecules. Now, when we transfer the ethanol into the water, right, we're going to create this solution if you have the interactions between the solute, which is the ethanol molecules, and the solvent molecules, which is the water. So we have those three types of interactions: solute-solute, solvent-solvent, solute-solvent. When you're mixing the two, the solute and the solvent, you still have all of those interactions. Okay? The water molecules, we have interactions between them. The ethanol molecules will have interactions between them. And then you do have interactions between your solute, which is the ethanol, and the water molecules. For a solution to actually be created, the interactions between your solvent solute molecules, they need to be stronger than the interactions that you have between the solvent solvent and the solute solute molecules. If the solvent-solvent, solute-solute interactions are greater or stronger than the interactions that you have between the solvent and the solute, there's no formation of a solution. Okay? The interactions between oil and water are not strong enough for you to get a solution. You have a heterogeneous mixture. You can actually look at the layer of oil, the layer of water in your container, because the two substances, they don't have strong attractions between these oil molecules and the water molecules. Since there's no strong attractions between solvent and solute, there's no formation of a solution. I'm just writing one molecule for water in each example. If you have a beaker with water, you have a lot more than one molecule, but just to simplify the sketch that I'm doing, I'm just writing down one molecule. Okay? And I have two compounds, very similar compounds, and I'm drawing this dashed line between the two ions representing that ionic bond between sodium and chloride and between silver and chloride. So on the left, I have sodium chloride. On the right side, I have silver chloride. With one of them, I can prepare a homogeneous mixture or a solution, and that one is the sodium chloride. With the silver chloride, I cannot prepare a homogeneous mixture or a solution. You have your sodium chloride, which is a solid at room temperature. If you transfer that in water, the attraction between the ions in your compound, right? The ion of sodium, the ion of chloride. The attraction between those ions and the water molecules is so strong that the ionic bond holding together your two ions, sodium and chloride, actually breaks apart and you get your solution. The attractions between this solute molecule, which is the silver chloride, and the water molecules are stronger than the attractions that you have between the sodium ion and the chloride ion. So you do get a solution because you can actually do this at home. You can dissolve a little bit of sodium chloride, which is table salt, in water, and you will see that it's a homogeneous mixture because it looks like just water. But the reason why the sodium chloride dissolves in water and the silver chloride does not is because the attraction between your ions and the water molecules is stronger in your sodium chloride solution. When you have the silver chloride, it's a solid at room temperature. When you add that one in water, the attraction between the ions silver and chloride is stronger than the attraction between the ions and the water molecules. So since your solute-solute attractions are stronger than the solute-solvent attractions, you don't get a solution for this one. So the attraction between the ions in sodium chloride and the water molecule, solute solvent, is stronger than the attraction between the ions. So you do get a homogeneous solution when you use sodium chloride as the solute. When you use the silver chloride as the solute, you don't get an actual solution because the attraction between the solute particles is a lot stronger than the attraction between the solute and the solvent particles. There is an energetic component on when we are creating a solution. So we can have three different steps, and they are listed here. We have separation of the solute molecules from one another. So those interactions between solute, we have to break those interactions apart. You have to do like separation of the solvent molecules from one another. So solute interactions, they need to be um, broken apart, right? We need to separate the solvent molecules, and then formation of those interactions between the solute molecules and the solvent molecules. So any any process that it's involving an amount of energy, right? We have two options. A process might require energy or a process might release energy. Any process that is releasing energy is known as exothermic. Any process that requires energy is known as endothermic. Out of the three processes listed here, two of them are endothermic, which means that they require energy. And then in general, or usually, the interactions between solvent solute molecules, those interactions actually release energy. So for the third step is usually exothermic. Now, just as a review, enthalpy is a name that we use for amount of heat. So when we talk about enthalpy, it's an amount of heat that it's absorbed or released at constant pressure. So when the amount of heat is absorbed, it means that that's endothermic. So enthalpy, which is amount of heat, right? We use H. And I'm going to write down here delta H. Okay? It's a state function, so it's something that we can measure looking at a final and an initial value. Okay? So we have that when a process is absorbing energy or heat, it's endothermic. The sign that we use for that type of process is a positive sign. It means that it's absorbing heat, so the amount of heat it's increasing. So if we're looking at a final and an initial state, right? If you have an initial amount of heat, but the process is absorbing heat, that amount is increasing, so your final amount is greater than the initial, and you have a positive sign when you have numerical values. When a process is releasing heat, right, we assign a delta H that it's a negative sign, okay? And that's based on actual numerical values. If you start with an amount of heat, let's say that you start at 20, right? Let's say 20 kilojoules of energy. And a process that has that amount of energy initially is releasing energy. So let's say that it's releasing 5 kilojoules of energy. So your initial 20 kilojoules, right? They're going down to 15 because 5 kilojoules of energy are being released. So when you do your final, right, which is going to be 15 because it's releasing 5, and your initial was 20, when you do final minus initial, you have 15 as the final minus your initial 20. That's going to give you a negative number. Okay? So any process that is releasing energy has a negative sign for delta H. Now, when we talk about amount of energy, amount of heat, right? We have these negative signs, but the negative sign is not that you have a negative amount of energy or a negative amount of heat. It's just telling you that the original amount of energy or heat is decreasing because that process is releasing that amount of energy. Yeah? So the overall process of creating a solution that involve these steps that are listed here, right? Number 1, 2, and 3, you can actually predict that sign for the delta H based on numerical values for the steps that you have, right? So the delta H is just adding the delta H's of all of the steps. When the separation of the molecules is happening, that's an endothermic process. It will be absorbing heat, so you have a positive delta H for this one. Positive for step 1 because it's an endothermic process. Positive for step 2 because it's endothermic, right? My step 1, when the solute molecules are separated, they will absorb energy. When solvent molecules, those interactions are broken apart, they will absorb energy. And then for step 3, we have an exothermic process. So when the interactions between your solvent molecules, when those interactions are being formed, energy is being released. So we're going to do an example now to go over the signs so you get to see with numerical values what's happening with that overall delta H value. So for my example, I'm using numbers. So these numbers are given, okay? So you have them. Step number 1, amount of energy that is required to break apart solute-solute interactions, right? It's an endothermic, so that amount of energy is required. We have units of kilojoules per mole for enthalpy. So you have a positive numerical value for the enthalpy, saying that to break apart these solute-solute interactions, 30 kilojoules are required for every mole. So that's like an amount of energy for my step 1. And since that's an endothermic, I'm still using the red color. Second numerical value is 20 kilojoules per mole. This is saying that that's the amount of energy that you need to break apart the the solvent-solvent interactions. So it's a positive number. It's an amount of energy that it's required for those interactions to be to break those interactions apart in kilojoules per mole. So that's my step number 2. And then step number 3, which is exothermic, right? It's saying that when the solute-solvent interactions are being formed, that amount of energy is being released. So the 60 kilojoules per mole It's a negative number because that amount of energy is actually released. So we're just adding the numbers together. We have the endothermic steps. Right? The first one, the second one, positive numbers. So those are absorbing heat. And then we have the exothermic, which is going to be the third one. And we can just add the numbers together to get how much the delta H is. The final number is going to be a negative number. You can do this in your calculator if you want. You have 30 plus 20, which is going to give you 50 kilojoules per mole. That's a positive number, and then you have plus negative 60, right? So your final number is going to be negative 10 kilojoules per mole. So this process actually happens. You will get a solution when these are your numerical values for the delta H, amount of energy that is absorbed and released. You have a net amount of energy that it's been released, which means that the interactions between solute solvent, right? You actually get energy when those interactions are being formed. Or in other words, the amount of energy that it's absorbed for to break apart the solute-solute and the solvent-solvent interactions is less than the amount of energy that is released when the solvent-solute interactions are being formed. There's an easy way of determining if the overall process is an endothermic or exothermic process. So if you want to determine what type of process is the one that you have, you can just look at a change in temperature. Right? So let's say that I have a beaker with water, right? And I have an initial temperature in my beaker. So my thermometer is inside the water, and let's say that that initial temperature is 20 Celsius degrees. So if I transfer my solid here, right, and it actually dissolves, right, it will dissolve and something is going to happen at that temperature. The initial temperature can go up or it can decrease depending on what's happening when your solid particles are dissolving in the water. So let's say that the initial temperature is 20, and then after all of the solid dissolves, okay, I transfer my solid. When everything is actually dissolved, let's say that my temperature now is at 30. So the temperature increased from 20 when you had just the water up to 30 when all of the solid dissolved. The change in temperature, and for change we always use that triangle with it's a delta, is the final minus the initial. So my final temperature is 30, right? Because I'm measuring what's happening to the temperature. I have an initial temperature, just the water. After all of the solid dissolves, the temperature went from 20 to 30. So my final is the 30. That's giving you a difference of 10. Okay? Um, as a positive number. Okay? So the temperature that you're measuring is the temperature that it's increasing when the solution is forming. So that's the temperature of the solution. The temperature is actually increasing because when the interactions are being formed, they are releasing heat. When your solute-solvent interactions are being formed, they're releasing heat, and that amount of heat is being transferred into the solution that you're creating, and that amount of heat is actually responsible for the increment in the temperature. So something that it's exothermic, or that it's releasing more energy when the solute-solvent interactions are being formed than the amount of energy that is required to break apart the solute-solvent interactions, right? That's exothermic. Just like the numerical example that we did. The difference in your initial and final temperature is going to be a positive number. The temperature is increasing, but not because the process is endothermic. The temperature is increasing because amount of energy is being released from that solute solvent interaction, those that formation for those interactions is releasing energy. Now that amount of energy is actually going into the solution and is responsible for increasing the temperature. So when you measure the temperature of a solution and the final temperature of your solution is greater than the initial temperature, it means that an exothermic process is happening, and the amount of energy from that exothermic process is actually responsible for increasing the temperature that you're measuring. When the opposite is happening, when an endothermic process is happening at a microscopic level, the endothermic process is going to absorb energy or heat. When something is absorbing heat, it will absorb heat from that solution and the temperature will decrease. Your final temperature is going to be lesser than the initial temperature because the process that is happening is absorbing heat. So the amount of energy is decreasing because it's being absorbed. You can actually measure the temperature of a solution. And if the temperature of the solution is decreasing, right, it's going down, your final temperature will be a smaller number than the initial temperature because the microscopic process that is happening is actually absorbing energy. It's absorbing energy from the solution, and that you can actually observe that happening when the temperature of the solution is decreasing.